no tears. So this is basically saying that he roots his Einstein roots his equations of general relativity in Riemannian geometry. There are standard geometry equations that he starts with. It's actually very simple. So Einstein did not like to overcomplicate people's lives and physics and things like that. He was very simple, like four-dimensional space-time, where one of the dimensions is time, the three are spatial time. So it's not your plane geometry, it's not Euclidean geometry, but it's a very simple Riemannian geometry. There's nothing alien going on. Somebody actually mentioned about aliens. There's no aliens in general relativity. Einstein was actually mathematically a pretty simple guy, okay? So were the fabric of space to develop such irregularities, so he didn't think that these types of irregularities were allowed, okay? Were the fabric of space to develop such irregularities, the equations of general relativity would break down, signaling some or other variety of cosmic catastrophe, a disastrous outcome that our apparently well-behaved universe avoids. This has not kept imaginative theorists. So by the way, wormholes, of course, appeared at first. Actually, I forget whether it appeared first in a fiction or not. It might have. But basically, the topics of that we discuss right now or going forward here is equally of interest in science as well as science fiction. So this is where science and science fiction can sometimes kind of overlap, okay? This has not kept imaginative theorists over the years from pondering the possibility that a new formulation of physics that goes beyond Einstein's classical theory and incorporates quantum physics might show that rips, tears, and mergers of the spatial fabric can occur. It's true, he did get a lot of help from mathematicians. It would be very difficult without that. It's true. He's much more of a physics guy than he's a math guy. But I mean, he's good at math, but for sure, yeah. You know, I think you're right. I forget. I sometimes forget all the names of the people that helped him, but for sure. So we will see if there is any ripping or tearing of space that's allowed. Not so in classical theory of space-time, not so in general relativity. So remember that general relativity is an update to Newtonian mechanics as far as gravitation. So sometimes I say Newtonian mechanics and I say classical mechanics, and I mean the same thing, but I should sort of correct it in the sense that general theory of relativity is actually also a classical theory, in the sense that it's not a quantum theory. So there is classical physics and then there is quantum physics, right? Classical physics is generally the physics of the big, of the scales that we understand, that we experience, and quantum physics is the physics of the very small, subatomic scales, very tiny scales that are difficult for us to comprehend. Now, Newtonian mechanics is the old classical mechanics, and general theory of relativity is the new classical physics, which describes gravitation. So it's not to be confused with quantum mechanics. Quantum mechanics is another whole world. Remember how this quantum world and general relativity did not agree is why there had to be, oh, thank you. These two, quantum world and general theory of relativity, do not agree is why we needed a grand unification theory candidate to begin with, right? So general relativity is classical, so it might not allow certain things, certain ripping, certain weird things, certain bizarre things that may be allowed in a quantum world. We will see what this has to say about that. But basically, string theory is trying to marry these two sides of physics, right? It's trying to marry the classical side with the quantum side. The general relativity side is the classical side. It's the new understanding of gravitation, but it's still a classical understanding of gravitation. And then quantum mechanics is the other side, which has no unification with this side. They're two fragmented parts of physics. And quantum mechanics is saying, well, we can describe the physics of the very small, and we're happy with that. Whether we seem bizarre or not to classical people, we don't care, because we have experimental success, and they do. Remember, all of particle physics came out of quantum mechanics, and if particle physics was not experimentally successful, then it would have been killed long ago.